Have you ever really stopped to think about how your computer thinks? I mean, how does it take a simple click of your mouse and turn it into a complex action, all in less than the blink of an eye? Well, today we're going under the hood to explore the fundamental blueprint that powers literally every single device you use.
Seriously, think about that for a second. You click an icon, a program opens. It feels totally instant, right? But in that tiny fraction of a second, this incredibly complex chain of events just fires off. We're going to trace that entire journey from your command all the way to the computer's action, and it all starts with the master plan.
You see, every modern computing device, I don't care if it's a massive supercomputer or the smartphone in your pocket, is built on a foundational design, an architectural blueprint. So let's take a look at one of the most influential blueprints in the history of, well, everything.
Now, this diagram, it might look pretty simple, but it represents an absolutely revolutionary idea from a guy named John von Neumann, the stored program concept. What does that mean? It means the computer stores both its instructions, the things it's told to do, and the data it needs to work on in the very same memory. This one idea is the basis for pretty much every computer we use today.
Okay, before we go any further, we need to get two key terms straight, because they can be a little confusing. First, you have computer architecture. That's the what. It's the set of rules a programmer uses to talk to the hardware. Then you have computer organization. That's the how. It's the nuts and bolts, the physical implementation of that architecture. Think of it this way. Architecture is the blueprint of a car, and organization is the specific engineering of the engine that actually makes it go.
So while that von Neumann blueprint is everywhere, it's not the only game in town. Turns out, there's a huge design challenge that's led to a completely different way of thinking, and it all comes down to one problem. How do you get information to the processor as fast as humanly possible?
All right, take a look here. On the left, we've got our familiar von Neumann architecture. See that single, shared path between the CPU and the memory? Now look over to the right, at the Harvard architecture. The key difference is staring you right in the face. Harvard has two separate paths. One is just for instructions, and the other is just for data. So, what's the big deal? Well, with von Neumann, since instructions and data have to share the same road, it can create a traffic jam. We actually call this the von Neumann bottleneck. But with Harvard's separate paths, it's two-lane highway, the CPU can grab an instruction and the data it needs at the exact same time, which makes it way faster. This is exactly why you often find Harvard architecture in specialized systems where speed is absolutely critical.
But hang on. The physical layout, the number of highways, that's only half the story. The other huge design choice is all about the computer's internal language, its instruction set. This defines every single possible operation the processor can do, and it leads to another massive debate.
And that brings us to RISC versus CISC. RISC, which stands for Reduced Instruction Set, uses a small, simple set of commands that run super fast. On the other hand, CISC, or Complex Instruction Set, uses a much larger library of more powerful but slower instructions. Now, check out the examples. The ARM processor in your phone, that's RISC, which is amazing for power efficiency. Your PC's Intel processor? Probably CISC, built for raw power. But here's where it gets really interesting. These lines are starting to blur with new RISC-based chips, like Apple's M series, now powering some incredibly high-performance laptops. The game is changing.
Okay, so we've got these different architectures, these different languages. But how do the messages actually travel between all the computer's main parts? Well, they need a kind of internal information highway system to get around.
And this is it. It's called the system bus. Think of it as the main communication backbone that connects everything. The CPU, the memory, your keyboard, your screen, everything. Every single piece of information travels along this bus.
But this highway actually has three very distinct lanes. You've got the address bus, which is like the GPS. It says where the data is going. Then you have the data bus, which carries the actual data itself. And finally, the control bus acts like the traffic signals, sending out commands and timing signals to make sure everything happens exactly when it's supposed to.
And now we get to the heart of it all. We've got the components, we've got the highway connecting them, so let's see how they work together step by step to bring a single command to life in what we call the instruction cycle.
For every single thing your computer does, its CPU repeats this fundamental four-step dance millions and millions of times per second. First, it fetches an instruction from memory. Then, it decodes it to figure out what it's supposed to do. It finds the address of the data it needs, and finally, it executes the command. Fetch, decode, read, execute.
It's this constant, lightning-fast rhythm at the very core of your machine.
Whoa, okay, I know this flowchart looks a little intense, but it just shows the decision-making process in more detail. See, after fetching and decoding an instruction, the CPU basically just asks a simple question. What kind of command is this? Is it a memory command? Is it an I/O command? Based on the answer, it follows a specific path to execute it, and then it immediately loops right back to the start to grab the very next instruction in line.
So when we say instruction, what does the computer actually see? It sees this, a string of ones and zeros. This binary code is broken into parts. The opcode is the verb. It tells the CPU what to do, like add or store or load. And the address part, that's the noun. It tells the CPU where to find the data for that operation. This right here is the true native language of the machine.
So we've been deep in the weeds with blueprints, languages, and highways. But why does any of this technical stuff actually matter to you? Because these architectural decisions directly, and I mean directly, shape the technology you use every single day.
The fact that your smartphone can last all day on a single charge, you can thank its power-efficient RISC architecture. Those mind-blowing graphics in your gaming console? That's possible because of a highly parallel architecture. Self-driving cars rely on specialized real-time architectures to make life-or-death decisions in a millisecond. And the entire cloud, from AWS to Google, is built on architectures designed for massive scale. The blueprint defines the capability. It's as simple as that.
And ultimately understanding this blueprint is what allows developers to create better software. Just look at this course syllabus from PCT. It says that knowing the architecture allows programmers to write code that's faster, smaller, and less buggy. It is literally the key to unlocking a machine's true potential.
From that original single-bus von Neumann model to the crazy multi-core processors we have today, computer architecture is always evolving. As we demand more and more for things like AI and huge data processing, engineers are designing totally new blueprints, things like open-source RISC-V systems and processors with almost 200 cores. So that really just leaves us with one final thought. What will the blueprint that powers our future even be capable of?